All right, so today we are talking about access control. In my continuing effort to kind of spread threat modeling throughout the slide, we're going to talk about an attack surface. So I realized when I was having the conversation about password managers, the reason we were kind of struggling is because I hadn't covered attack surface. So let's talk about attack surfaces very briefly. An attack surface is all the stuff you're trying to protect that could be attacked. I mean, there's some more complicated definitions you can get out there, but short, it's just all the stuff you're trying to protect. Now, if you look at this beautiful castle photograph that you see here, there's a lot of things they were doing back during castle design to reduce their attack surface. I mean, look at this. There's this lovely drawbridge. These don't look like nice windows, but they're doing a lot to protect the attack surface of this castle. As a broad statement, the more you are trying to protect, the worse your life gets. So just as you add more stuff, everything gets harder. Reference back to our just news story. Most of you probably aren't thinking about the advertising libraries that are sitting on your phone. Every advertising library helpfully added by an app developer is increasing your attack surface. I'll come back to this example later in this lecture, but if you buy tickets to stuff, I tried to get a movie theater picture, but I couldn't grab it quickly. Right, you go to the movie theaters, you buy a ticket at this front gated thing, like there's a glass window, someone takes your money right there, and then happily they give you this little tiny sheet of paper. And you can go wander into whichever of the movie theater spaces you'd like. And this, you can use the paper here. What are they doing? They're reducing their attack surface. They're basically saying, let's put all the security effort behind that one place that's managing money. And now all of our highly distracted employees really just need to pick up this piece of paper and go, is that the right movie name? Yes or no? And they don't need guards around them. They don't need to handle money. It's an attempt to reduce the attack surface of a movie theater. This is done all over the place. When we talk about password managers, it's getting a lot more complicated, but it explains why I have the opinion I do that password managers are better. Because what they are doing for the average person, which may not match your model, but for the average person, they are reducing the attack surface. Because what they're doing is that each login is now guaranteed to have a unique and strong password. And we're giving two models here. Either a website is compromised. If that happens with a password manager, then only that website has been compromised. I haven't lost the password for anywhere else. And two, the password database gets stolen, which is bad. But one, we put all our security right there. We don't just random people run password databases. Please don't use a startup or a password database. Pick a company that knows what they're doing. And two, if you actually put all of your brain effort behind memorizing one complicated password, it's now actually really hard to break that database. You can't just pull it down and use it. You've got to pull it down and you have to crack that password. Compare that against a user required to memorize all their passwords. Zephyr. So they take easy to predict passwords because they're easy to remember. They reuse their passwords. I mean, you don't have to raise your hand. Everyone think, do you have a minimal security password? That password you put into everything you don't care about? If it's compromised on a single website that you thought wasn't very valuable, every single thing you didn't care about is now compromised. And websites grow. That Twitter thing, you used to think, what the heck is this? This will never go anywhere. Maybe that went somewhere. So your threat model now is that if there's a website compromise, particularly a low security website, you've now lost everything. Because your attack surface now is every single website that has that password. And your other problem is password guessing, because now you have a predictable non-random password. It is possible that someone's guessing it. And again, we talked about lockout, right? Lockout is done per website. If you use the same password on 7 websites, I can now guess your password at 7 times the speed. I just try it on a different website every single time. This is why for an average user, password managers are better, because they reduce the attack surface and they center it on something that actually does security for you, as opposed to say your coffee shop, which hopefully is working on coffee still. All right. Sorry. I have not dug into Snapchat, no, but their surprising things are the biggest things. All right, this comes on to two paradigms. We're going to yep. Sorry. Did the mic turn off? Thank you. Remind me when I do this. Okay, there are two big philosophical approaches to security. You kind of see this playing out from the attack line. So just generally think about it. One of them is capsule type security. This is the way the military thinks about security. The idea is that you have a perimeter and you throw all your energy into guarding there. You put a lot of effort on those gate guards. You put a lot of effort into going and making sure that no one passes that front gate without being appropriated. Maybe you have curtain walls where this is the minimal security, more and then more security. But the point here is you're throwing all your resources into having security professionals who know what they're doing, being in charge of security at the edge. And then everything inside has got at best minimal security. It's assuming that you couldn't have gotten past the gate without this. Maybe there's a bit, but not all. The other way you can do this is think of this more like an open entry village. Most of your houses are probably like this. You do not have armed guards sitting outside your front house. You just have a standard issue lock. You're kind of hoping that really, really skilled lock pickers don't bother trying to attack you because you're just not worth the bother. But this is a situation where every person makes a decision for themselves. You know, like, do you need 6 locks? Do you need 1 lock? I have relatives that seem to don't believe that locks need to be locked. I mean, everybody's a bit different. But the idea here in this model is each thing is protecting itself. This is sort of better because now we don't assume that everything is safe. But it is also worse because we have now put people in charge of security that are no good at security. Because they just have this skill. And so these are kind of two different models of how to approach it. They both have weaknesses and strengths, and you'll see this kind of play out. We are not networking. I just wanted a networking example of this, since we're mostly talking about capsules. Networking works a lot like this. All your traffic's coming in across the router. We haven't learned a lot about this yet, but there's a lot of security sitting on that router for a reason, because it's taking kind of a capsule security approach to this. Your computer, when you go and you connect to, say, a wireless network or wireless printer, for example, are you on a public network? It's a terrifying thing. What is it asking? Where are you sitting? Are you out here or are you in there? Because if you're in there, things are safer. So this is capsule security. As opposed to devices that are maybe trying to handle a whole lot of attacks from the open internet because they have fixed IP attacks. Okay. I'm going to get off the high theoretical components here. And we're going to move down to access control and information flow control. Today we're mostly going to be talking about access control, but I'm going to introduce both of them now, and then we'll get to information flow control. Either if we go fast today, we'll get to it today, and if not, we will get to it on Friday. All right. So a security policy describes the requirements for a system. So what is it the system should do in terms of access control? And a security model is a framework under which that policy can be described. The difference here can be a bit similar to our example just 2 seconds ago, where I talked about 2 philosophical approaches. Neither of these actually describe for this person, should this person be allowed in? But they are 2 ways of thinking about the problem that then cause you to make decisions. So a model or a framework is intended to be a different ways to think about the problem. And then the policy itself is more this person should get in here, this person should do that. So it's more specific. There are 2 basic paradigms for these kind of high-level concepts of how we do this. One of them is called access control, and the other one is called information flow control. And in an access control, a guard controls whether the principal, which is the subject, you might think of this as the user, but we're going to talk about a lot of other things you can access, is allowed to access a resource or the object. You might think of this as a file, but again, keep in mind, you have printers, you have a screen, there's a lot of different resources out there. And so the idea here is that we start from the subject. They make access requests, it goes to this thing called the reference monitor, they'll explain in a moment, and then they gain access to the object if they're allowed. Information flow control spins this room. We're still talking about a guard, we're still talking about subjects and objects, but now we're starting from the object. So the idea here is that an object, which is in information flow control, we're carrying a lot more within the object, so you might even think of this as information. We take that information and we ask whether or not this information can be known to this subject. This is horribly confusing. It confuses students every single year, which is why we're going to have an entire lecture on information flow control on Friday. They are different. They start from different places. And this will make sense when I spend a whole lecture on it. But I do want you to keep in mind there is this duality and kind of start thinking about this as we discuss it. All right, and I'm sorry, I know it confuses people every single year. It took me a long time staring at a wall to get it not to it. We're going to start with access control. Access control is the one most of you have some clue about already. You've already had this problem of, can this person see my posts? Who's allowed onto this computer? If you've actually been on a Linux server at some point, can I access this file? Usually day one of being an intern is all about access control. Can I get access to this thing, to that thing? Oops. Oh, this Slack. No one's added me to that yet. Most of you are familiar with the general concept. Access control is predominantly done off of 3 points: the subject, the object, and the access mode. The subject is who or what is doing the access. That could be a person, that could be a process ID, that could be a network address, that could be whatever it is. The thing doing the access. The object is what is being accessed. Sometimes we also call this as a resource. Is it a file? Is it the screen? Is it the mouse? Is it a robot? Is it the printer? I mean, there's all sorts of things we can access. Is it the servos that make your car wheels go? All sorts of things we can access. And the access mode is all the different things you can do to that object. And I'm going to double down on that one in a moment. Okay, these main points. I will give you an example. It does not matter what Figma is. All it matters is that I attempted to go and use Google, sign in with Google with it. When I tried to sign in with Google, this thing popped up. It says that I'm about to sign in Figma, and by continuing, Google will share my name, my email address, language preferences, and profile picture, and any future updates to those with this person. They are making an access control statement. They're saying the subject is Figma, these are the objects which have been listed to me. They don't explicitly state it, but this is read access. And it's basically saying, would you like to create this access control rule? Yes or no. I'm going to talk about, okay, so subjects and objects, this group should get it set up. I'm not too worried about you. Access modes always seem to hit people upside the head because you're kind of convinced that read, write, execute are the only things that exist. They are not. On the bottom here, I have a list of all the controls you can get in Windows, and that's actually not all of them, those just the ones that are visible. Read, write, execute, sure. You can also delete, append, create a file, create a folder, see folder contents. You can decide who has permissions, who has the right to change ownership. All of these things could be individually pulled out and managed. What about the ability to read a live update feed? Right now, you upload all your stuff probably onto CrowdMark for the majority of your classes. Back when I was a child, we used to go and all push it onto a folder we couldn't read called a Dropbox. They named it after something. So the idea is that you could write to it but not read. And so, and if you look at some of the ones on the Windows, it has things like traverse folder. So maybe you need the ability to traverse this folder without reading the folder or writing to the folder because you need to be able to get to the subfolder. So there's actually a lot of different access modes out there, and this is just sitting on the file. We start talking about things like robots, printers, all this other sort of stuff. There's actually a phenomenal number of access modes out there. All right. Okay, are there questions on subject, object, access modes? a laudable goal no one ever hits, but it's important to know. It's called the principle of least privilege. This means you shouldn't give people access to stuff they don't need. There's this behavior you get in companies where as you slowly rise up through the company, the number of files you have access to grows, and people's willingness to take it away from you also decreases. Like no one wants to take information away from the people who make security. This is a good way to go and get a lot of things hacked. Because they know who to target, right? They don't just target the boss because he is or she is making a lot of money or in charge. They target them because they realize that people who come up through the system just start collecting more files. As a general rule, you want to make sure the subject should have access to the smallest number of objects necessary to perform their tasks. This is why Windows, long ago, used to make you elevate yourself to system administrator in order to do anything. Because they were trying to get you to have principal of least privilege, which is what most of you don't want on your own computers because it's annoying. But again, it's an attempt to kind of reduce this. This means that we should either be moving or adjusting permissions over time. So when someone shifts jobs, they should actually lose access to the old stuff. We should make sure that files are given, or even processes are given access they don't need. So there's an example at the top of it related to may require a bit more knowledge of processes as we taught thus far, but this idea that even a program, what does the action need access to? Does it need to know the actual physical memory address? Or is it sufficient for it to have a virtual memory address? There's just all sorts of places where you can actually remove information that is not necessary. And by removing it, that means that if the attacker breaks into that one thing, they don't break into everything. So again, this is an attack surface reduction. You're just trying to say, do you really need this? You don't need this? Let's kind of take that away so you can't cause damage. You can remove or readjust, or the other one is soft removal of privileges. So you see this at some companies. If you don't use your privilege for a little while, it gets soft removed. That means you do still kind of have access to it, but to get that access back, maybe you have to go through a multi-factor authentication process. Maybe you need to have your boss just tick a box really quick to get access back to that object. I mean, it comes back easily, but it just naturally reduces when you don't use it. The most classic example of why we do this is ransomware. So what happens in ransomware is you download this file, thinking that it's something safe, but it is not something safe. You run it, and then the system goes and it finds every single file you have access to, usually over the course of a couple of weeks, maybe even months, and then encrypts everything. It can't do it with the soft removal, right? Because it'll flag a multi-factor authentication attack. And it wants to be quiet. So things like soft permission removal will just reduce the number of files that could be attacked, if stolen from an attacker, if someone, say, falls for a scam because of that hacker. Again, this is just the principle of least privilege. Here's a really basic example. This is an elevator in a hotel. In this elevator, you can't get to a floor unless you have a hotel key for that floor. So you tap on the thing, and then you can click on it. If you try to click on a different number, won't let you go. Very simple example of principle of least privilege. And this is the ransomware example. And yes, this does happen. It just installs itself. I gave an example on news the other day about somebody who wiped out a shocking number of databases in 5 minutes after being fired. Again, this is another example of a principle of least privilege. If someone is no longer working for your company, they shouldn't have access. This is another example of a news story. This one just said this former employee stole 700,000 company records and was happily selling them to no one knows for years. Okay. That's the principle of least privilege. That tells us everything should be narrower, but if you start in on trying to set out access to everybody, you'll go mad. Like, should you have access to this guy, this guy, this guy, this guy, this guy? I mean, it's crazy. So usually you want to approach this with some sort of very high level strategy on how we give access. Now, researchers have worked on this for a long time in nice ivory towers, and then system administrators work on this a lot from down in the depths, trying to make everything actually function. And And then somewhere in the middle, we find several approaches. So the researchers all concluded for a long time that there were only two approaches to this, which we call MAC and DAC. So MAC, okay, we'll start with DAC. DAC is probably what you're more familiar with. It's the idea that the owner of a file, whoever owns it, should be able to decide what to do with it. This is similar to village security, right, where everybody kind of makes their own decisions about security. The owner of the resource decides who can access that resource, what they can do, and they set a policy on a case-by-case basis. That means the policy on this file may be radically different from the policy on that file. How one gets access to this may be radically different than how one gets access to that. This is all handled discretionary, with each individual making this decision and the system administrator having very little overarching understanding. This is awesome for getting stuff done, because now you just poke the guy next to you and go, hey, could you please give me access to the Slack? And they just do. And this is very bad in terms of things like auditing and making sure that corporate policy is followed. The inverse of this is mandatory access control. Mandatory access control is straight out of the military. The idea here is that the decision of who gets access to resources is system-wide, and it's a uniform policy. The system administrator or someone in that position just says, okay, this team access to those team folders, this team access to that team folder, and that is how it is. And if you would like to go and add someone to your team, let me know and I will add them. And you will not be adding them yourselves. Okay, so MAC is kind of top down, discretionary is top up. These are the two classic examples. You'll find these in most textbooks. I'm going to throw two more out at you. These are two different approaches. So for a while we thought it was only MAC and DAC. And then after a bit we said, I actually dug up the research papers, like 60 pages long, in which someone had actually gone out and asked the system administrators what they've been up to. And concluded that they had not used MAC or DAC the entire time that the academics had been theorizing, and instead wrote this thing called RBAC. RBAC is role-based access control. It actually looks a lot like MAC, mandatory access control, but it's kind of got this middle ground component. So the idea here is that each user is assigned to a role, and each role is then assigned to maybe a file. So if you are a finance manager, for example, there might be a finance manager role, and then files are given access to the role. So the idea is this is a list of users who are finance managers then have access to these files. And so this is role-based access control. It's possible for somebody to be in, say, more than one role, and then the idea is that you can manage all of this without having to do user file for a full company. Attribute access control is becoming more of a thing. So the idea here is that each file, or maybe person, has an attribute of them. This could be a tag, it could be metadata, all sorts of things can be used for this. I mean, I use a system for paper management that is based heavily on tags. So tags can only be set by the admins, but whatever the tag is actually massively controls the access control for the file. And so the idea here is now I give access based on the file itself and what tags it has on it or what features it has on it. So a really simple example of this is if you join a chat channel, depending on the chats. Sometimes it will say, oh, no one has access, the new person will not have access to the old chats. This is closer to attribute based. It's basically saying, okay, I just take all the chats and I say, actually, this person will only have access after this time frame. I'm mostly giving these to you as counterexamples. There are a lot of different ways to do this. I'm not really going to dive into this at great depth. I don't expect a lot of people to know this long term. But there are a whole bunch of different ways to think about how do I work. I also want to point out that you're thinking owner. Yes, I'm the owner of this computer. I am me. And then you type sudo. Are you you anymore? Who you are is shockingly flexible from the perspective of that computer. You may be you 1 minute, or for example, in a different system where I work in, I have the ability to pretend to be someone else. I can do that because I'm the admin and I need to be able to do that sometimes. But I can sit there and go, oh no, I'm Abby. And now I'm Abby. resources can be principals in the system. They also may be controlled themselves. And the identity of subjects is more flexible than you normally think. So SUID programs in Unix, sudo command can be used to change who you are. So principal is not as fixed as you might necessarily think. Okay, now we're going to hit a slide you're going to hear about a lot. All of access control is based on this concept of a reference monitor. Reference monitors, the way they are presented on this slide, are horrendously theoretical. You will not find the reference monitor within Linux, but you must have something that fulfills this requirement, or it just the whole thing falls apart. Access control only works if there's some component in the system that is always invoked. Every time an access happens, this thing runs, period. Every single time. If it doesn't happen every single time, that's how the route the attacker will now be taking. I showed a news article a couple days ago about a journalist that had hacked a system by just finding the API calls that did not access the reference monitor. That was easy. Immune to tampering. I know this is a hard requirement, it's almost impossible, but this thing needs to be as hardened as we can get it. If it can be hacked, it's all over, it doesn't matter, we can't control access. And it needs to always be correct. This means that partially determinism, but also means that you need to make certain that the coding sitting behind this thing is doing what you think it's doing. And again, if it's not, you have a big problem, you can now go around the access control system. Another way of summarizing this slide is there had better be a thing in your system that every single time someone tries to access a file, it must go through the thing, and the thing is accurate in saying whether or not they can access the file. And if you don't have this, you don't have access control. And we call this a reference one. All right, for simplicity, I will now be talking about operating systems. Almost everything I'm about to say could be mapped onto your favorite weird system. But just for all of our sanity, we're going to talk about operating systems. Keep in mind there are things like, so an operating system will, let's pick on Android for a moment, right? If you have an app, that app is accessing local Android resources, but that app is also accessing resources that from Android's perspective just belong to the app. But from the app's perspective, actually, there's a lot of differentiation internally. Like this might be its system files, and these are your messages, and these are your messages that must be exploded after 3 minutes. And so the app itself may have internal access control, and then the operating system itself treats that app almost as a singular unit and does its own access control. And I'm just simply pointing this out that you can get kind of these layered access control situations, and I'm not going to go there very much. I'm just warning you that what I'm about to show you is the easy stuff. So how does an operating system manage permissions? It needs to decide what user application process ID is allowed to perform actions on resources like memory, devices, printers, all the stuff attached to that. And that means we need this kind of low down. We need to make sure that the user can't muck with it. We need to make sure that individual programs can't muck with it, which means it's kind of sitting closer into the kernel. And the further down an operating system you move something, the more it slows literally everything down. I want you to think about just how many files per second your computer is accessing while just sitting there. A lot. And if every single one of those must go through a reference monitor, oh man, that sounds bad. Especially when I care about speed. This is why you see sometimes big, enormous servers turn off things just so they can go faster and then discover why we turn them on. So things like lookup speed, they also need a clear answer. If you go and ask a question about privacy over in social sciences, they'll have a nice debate for the next hour over whether or not someone should or should not have access to something. We can't do that. When you access something, it must be a yes or a no. There's none of this like, well, maybe. Well, is it Tuesday? Yes, no, fast. Because we need speed. We are always considering the costs here, but keep in mind that everything has different access patterns. So we talk about cost, but where should the cost be sitting? Is it maybe cheap to read, but more expensive to write? Is it, where is the cost? I'll talk about cost in the development side. And also considerations like storage space, stack, Mac. We have to kind of consider all of these in the setup slide. All right, that was the higher level theory, and now we're going to start talking, not actually implementation, this is more whiteboard level implementation, but we're talking about how to actually build this stuff. And again, you've all been thinking about Linux your whole probably time, but we're going to think about this thing. The first year I taught this, I looked up at the audience and was like, you're in headlights. Like, I just can't absorb that much data. And so I've started doing a peek at the thing fair share. So I'm giving you this ahead of time so that you can think about it over the next couple of slides and help you organize the information I'm providing. And then we will do this as a think fair share thing. All right, I have created this FooBar app. It's a completely irrelevant app. It does serendipitous photo sharing. Serendipity is good things unlooked for. You haven't heard the word before. So the idea here is that users can take the photos as a cute squirrel and upload them. The system then grants access of the photo to a randomly selected 5% of the other users. So I just grab 5% of other users. Here you have the photo. Serendipity. The users can request edit access to photos, which allows them to retouch those photos. So the question here is, of the ones I'm about to present, which of them is best for this situation? Okay. All right. So now I have this broad problem. There's all these users, subjects out there. There's all these objects out there. Both of those sets may be large. How do I state who has access to what, such that I can do fast work and be clear every single time? Do they have access? Don't they have access? This sounds so simple. It is harder when we try to build it. One of the early approaches is something called an access control directory. It might be helpful to think of this as the way maybe Google Drive does this, or some way OneDrive does this, where you can pull up every single file you have access to. Now that's a virtual folder, isn't it? It's not real, but it just shows everything you have access to in your folder. So the idea here is that we have every single user. Every single user basically just has symlink files. And if they have access, the file is in their folder. And if they don't have access, the file is not in their folder. And the things in their folder list kind of the read write. That means we can do speed now, right? So this looks vaguely like this. So you have user A here. They have this directory. They have access to these files. For each file, we have, I think O means, for this lecture part of it, I'm just doing owner read and write. For keeping things simple. What you're looking at here is just pointers. So what's stored here is just the names of the files, the permission, and so the idea here is now just every user, every directory, you're already in the directory is already loaded. This is nice and fast, right? And it looks clear too. But we can have a problem. What if there are two symlinks to the same file? One has read, one of them has read write. We have now broken one of our rules. It must be the case that you always know yes or no. What is going to happen when this person tries to write? We have a problem is what's going to happen. And so you can have problems with this granted twice, especially if a person's actually listening twice. So if you've ever been on Google Drive, I think you can actually link to the same file twice. And it's actually really harder. I don't want to get into it, but it's actually very hard to pull. Because it's possible that you link to something and then someone else links to what you link to, and you actually end up in these weird chains. Okay. Well, maybe we're just trying to over-optimize this. Let's make certain now that it's only the case that each file has only one set of permissions, right? Then we can do our yes, no, either. The most obvious solution to this is to create a matrix table. We're going to go put all the users down on the rows, all the files in the columns. Oh, beautiful. Beautiful lookup speeds. Absolutely very, very clear on who has access to what, because there's only one spot to write it. You can't have differences of opinion. Your biggest problem here is that this thing is sparse. Most people don't have access to most files. There's whole chunks of your operating system that are only accessible to an administrator or sudo for good reason. And yet every single user is now got that space. But any single user could be given access to it, so it's not like you can just chop it off. And so this is kind of nice, but wow, is it just too big. But you'll see this one come up a lot because it's easy to understand. So often when we actually present permissions and we're trying to give examples, we'll put them in a matrix because the matrix is easy to This is a more formal version of the matrix. So the idea here is A is a set of S subjects, a set of O objects, so those columns and rows. Our model, an A operation, so A being the access mode. The idea here is that A in this case is only read write, which is what we're using it here, and the matrix is just a combination of those points. So you can do subject, you get an object, you look it up, and you get an output what's stored there, and you can access. All right, our issue is sparsity. What if we just turn this into triples? So now what we're going to do is we're going to go put the subject on the left column, the object in the middle, and the access right on the right. Now we be sure that our triples are unique. So it's never the case that you actually have a user object combination that is duplicated. So we'll do a lookup, we always make sure. Well, the blank ones, we just don't want. All right, now we are starting to hit the space where we're talking about access speeds and the difference between things. So if I want to do a lookup on this, it's annoying. If I've got it well sorted, maybe I'm looking at a big old login sort of situation. But you have to do a full lookup, and then you have to write if you want to give a new permission. So a new permission is actually expensive to add. The lookup here is also rather expensive to add, or do, because you have to do this lookup each time. But we still have our principle of that everything one answer. It's never the case that I look up something and I get two answers. Okay, well, it's annoying that we both got something more beautiful here, but it's not working so nicely. Let's try access control lists. This is probably the thing you've heard about most before. It's very commonly used in operating systems. Now how about instead of making, because in this last one, this triple, I was doing it for the whole operating system. So the whole operating system, I was looking this up. Maybe what I should actually do is organize this by file. So now what I'm doing is I'm taking one of these columns. So I take, say, help.text, and I grab every user associated with here and all their access modes, and I remove all the empty forms. And I get this. So now I have a directory here, and for every file in the directory, I have an access list pointer. This pointer points up to a list of users and a list of permissions for this file. This is, I'm going to just move back again. See the help.text right here? I've just taken this column and the user column, put them together here per file. So F, for example, has a little lookup table, diblog has a little lookup table. All right, so now what I've done is I've co-located the file with the permissions. All right, this is actually kind of nice now. Now I still have my triples. Assuming the user is trying to access the file anyway, I have to access that part of memory anyway to give them access to the file. So I can actually access that and then get the access control list right there. It's much easier to say maybe add someone's permissions to this now. Again, I keep the file, I can wonder if they're not on there. I still have my property that I know whether someone has access or not, and that I don't kind of have this weird back and forth. Each user is listed at most once. All right, that's all good. But I have just made deleting users inactive. What happens if I have to delete a user?
You need to basically go through every file. The other thing you can do is have a master user file that points to every file their menus in, which again there's another file
I
that
still have to go through every file just to find them faster. Yeah, I now have an O of N problem. I must go through every single file. The suggestion in the front row is it's possible I have a little sneaky back file that tells me what files anyone has access in, and that might help me do it faster. But I basically now have to comb through my entire computer to delete things. But think about it, how often do you change permission?
user for
I just like I'm back.
is user for
So it's each user here is like Sue logs like a username. I'm trying to do this as the way that's most visual to you, or the way you're most familiar with at the moment. This could also be process IDs. It could be other things that are within the system, but predominantly it's users. So usernames. I'm just using user A, user B, system manager, user security, Apache. And so the idea here is that help.txt can be accessed by users A, B, S, system manager, and user sec, and no one else. Fast lookup for read, fast lookup for write, slow lookup for delete. If I want to delete a user entirely off this system, very annoying. If I want to change the user permissions for an entire folder, O of N. But this is the sort of stage we now hit where we start asking ourselves, well, what did you want? Because if I back this up, if I'm in an access control matrix, oh man, this is faster. If I want to delete a user, bye-bye road. Much faster. All right, I'm kind of trying to push you through this. Kind of think about all these, and not just say, oh, access list is the best. The other thing we see a lot in access control is what we call wildcards. So I'm listing a whole bunch of. It's possible that I want everyone to be able to read help.txt. That sounds actually a very useful file. Maybe I want every single user on the entire system to have help.txt. Listing every single user is a complete waste of space. So sometimes you will see access control lists have wildcards. So star here. Basically means that this user has ownership, this user has read write, and everybody has log. Does anyone see the problem? What was one of our properties we've been kind of pounding on? Huh? It's a little bit least privilege. That's not really a problem, assuming you did this on purpose. That says read right now. What does the top one say? Owner. One of our properties thus far has been, I need to know whether or not someone has access. So, huh? Yeah, well, so the problem is that that top user things has ownership, but they don't have read write. And putting that star there that gives them read write, or gives them read. Now, if I meant to do this, it's fine. And if I didn't mean to do this, this is a big problem. So it depends a bit actually on how you're structuring things. But this is one side effect. You'll find that in most access control, it's only a positive statement. So when you say, oh, I'm going to deny someone access to something, what we actually do is go through and just remove your access right. We don't actually have a negative access. Because if we have negative access, the whole world gets more annoying. Depends how this operating system is defined. I have a totally fake operating system here. So in theory, yes, they could go and grant access to other things. They could do it, but they haven't yet. And because they haven't yet, we are looking at a situation where it is potentially unclear. Is it the case that they only have ownership rights, or is it the case they also have read access? In most access control systems, it's additive. That means that if you're in a situation in which everyone has access and you don't, it will combine. Not always though, it's dependent entirely on personability.
So then in the example you were giving earlier with social media, if somebody's blocked, then would that mean that the server would have more difficult time figuring out where they're able to, like what the block user can actually see, or is that something that you maybe have like a block list for a user and then filter that through?
I have no idea how the social media companies are handling it. Usually when we're talking about in terms of operating systems, you have such a fixed short list, version of short list, that we don't really want indications because of okay, we have three things in here, they're nested. Folder A, folder B, file C. If I say no access on file B, and yes access this file, do they have access? It depends entirely on how this was implemented, and we now all mostly have a headache. As a side effect, you'll see most operating systems avoid negations like the plague, because they just don't want to deal with these conflicting states, in which this one says no access, that one says access. Well, maybe should they have traversal access? Like, what's going on here? Did this person mean to deny everything below? Did this one mean to allow to punch a hole through the thing above? Trying to understand user intent here is a little nightmare. And so as a side effect, a lot of access control systems just simply do not allow negation. This comes around to your point with the social media. Social media is not structured this way. Sorry, social media is a lot more structured as a flat model. You're talking about each individual post. Now, because you're talking about each individual post, you can pull negation off because you don't end up in a situation where you have two conflicting concepts. I'm trying to figure out from the eyes whether or not I've just horribly confused you or enlightened you. The problem is determining user intent. And if we can accurately, well, one problem is user intent. Intent assumes one person wrote both of these. The other problem, especially if we're now talking about a system that is mixing Mac and DAC, did a Mac person write this, an admin pushing down official policy, and did an end user write that? Who wins? Is it the administrator who wins? Is it the end user who wins? And again, as a developer, broadly speaking, you don't want to be there. And so as a side effect, again, we tend to just make positive statements only. You can build the negative ones. If you're going to go do that, do some research first about the things that are going to happen. But this is why, especially in things like Linux, you can have permissions or you can not have permissions. You can't have negative. Alright, this is just a screenshot of Linux. I've most of this work, I've seen this before, but I'm putting it on the screen anyway. Because we are now looking at an access control list, but this one's different, so I'm going to splash back here. This one is infinite length, isn't it? We have, actually go back further, we have like 5 different users here. This is annoying. You have to access the file, you have to follow the pointer, you have to do all this stuff, right? We don't like doing that. Linux has solved this problem by basically saying there's a user, there's a group, and an other. Each of them get permissions. And now, wow, it's this nice fixed length distance. I mean, the nice fixed length small thing, I can access it really, really super fast. I can do lookups super fast. And I can do that O of N deletion super fast. But I lose a lot of flexibility. And that is where we get groups from. Why groups though? Because this is an RBAC system. It's a role-based access control system philosophically. You can go and treat it however you'd like. You can make groups for friends instead of roles, but this is designed effectively as a role designed such that you have a group, and that group lists everybody of a certain role. So now you have the owner of the thing, what role is supposed to access this thing, and how everyone else on the computer is supposed to access this thing. And this is them trying to basically build an access control list, but removing some of the negative aspects of it that they're particular to their expected use case. They don't expect a lot of very complicated needing to link this person to that person, but not this other person when they build it, which is true for an operating system. Because as I mentioned before, you have an application sitting on top of that operating system, and then you have the operating system itself. The operating system itself maybe isn't trying to control a lot of this stuff, it's letting the application sort it out internally. Because of their model at this point. Windows also uses an access control list model. Man, they made it more complicated. This looks a lot more like what I was showing you before, right? Where you have all these different users, it's an infinite list. And it just says full access here, full control. Yeah, that means all these boxes look empty. You can go in and set all sorts of weird things on Windows. And we haven't even hit the tab called audit. You can also get audit permissions where you can't see the inside of the file, but you can see that its existence. So a lot of variations. All right. Any questions?
How can you be owner and not have return access to that?
How can you what?
How can you be owner and not have return access to that?
You can be owner and not have rewrite access because you can grant it to yourself later, but you don't have it now.
So the access you have is attribute.
Let's describe this as not wanting to shoot yourself in the foot. There's a lot of very simple things I do to not accidentally shoot myself in the foot. If I have a hot drink, I like to put a lid on it. Now I could drink much faster without the lid, but the lid is there to prevent me from harming myself on accident. There's quite a few files on my computer I don't want to accidentally write. Now I could grant myself access at any given time, but I don't want to accidentally write them. You probably run into this experience where you download an executable off the internet, and the first thing Linux does is helpfully make it read-only. Again, it's ensuring you do not accidentally run something potentially dangerous. You have to sit there and go, I am owner, make this executable. So you can be owner and not have this access at this exact moment from the perspective of the reference block. However, you can still be owner and have the ability to give yourself access. All right, we're all now going to think about this. I'm going to represent this. You're going to get 1 minute to think like normal, and then you can chat with your neighbors, and I will frantically remember what on earth I meant to correct activity. So this is a big picture. Imagine you're building a new foobar app for serendipitous photo sharing. Users can take photos and upload them. The system then grants view access of the photo to a randomly selected 5% of users. So a random 5% of users can now see this photo, no one else can see the photo. Users can request edit access. They don't have edit access by default, but they can ask for it and get it, which allows them to retouch the image. I think they are all editing the same image. I don't think I ever explained this. It's not going to fork copy, so they're editing the original version of the image if they're giving it away. Original uploaders can delete images, other people can't. What access control implementation is the best in this situation? I heavily encourage pulling up the slide that's looking backwards. When you answer this question, consider things like user count, resource count, where is the reference monitor here, and the frequency of permission changes. All right, 1 minute. Quiet, think to yourself. Okay, how are we doing? Oh my, we have like 5 minutes left. All right, we're definitely not getting the information flow. Let me talk briefly about the confused deputy problem. So up till now, I've just been assuming that we know who the users are. We spent 2 lectures on authentication we're kind of hoping we've got that all sorted. We know how to authenticate the user. So in theory, we should be looking at the correct user. How would that not be the case? Well, it's often the case that you are asking something else to do something on your behalf, and that something else may have more power than you. We sometimes call that a deputy. Here's a really simple-ish thing. So imagine Alice and the compiler have different access rights to the file build. So maybe Alice is allowed to execute the compiler, but she's not allowed to see the file build. The compiler itself, which can be an entity within the system, has the ability to read and write itself, read and execute, and it has the ability to write to build. So Alice simply tells the compiler to go and output all of her stuff into build. You may sit there and think, why on earth would this be the case? But remember I talked a lot about the ability to do things like a pen? A lot of programs need the ability to write to the system log, even if the end user doesn't have the ability to write to the system log. So there's a lot of cases in which you're accessing an application that application has more access than you. And we call this a confused deputy problem, in which you are asking the system to do something, and sometimes you can use that to escalate your privileges and cause confusion. So in a well-designed system, this shouldn't happen. But this means that when you're doing access control tracking within a system, you can't just track the users. You also need to track the user's activity, what they're accessing and code. In this case, maybe they're just trying to overwrite something. Oh no, ignore the normal system block. Use this system block. And then overwrite it. Alright, capabilities will take me longer than I have available. So we will be covering the remainder of this lecture on Friday. So I will see you on Friday. 3 minutes early. I can't communicate capabilities in 3 minutes.
So what's the solution? Is there a solution?
To what?
To the confused problem.
Be careful. Like, think about it when you build your system.
So the control mechanism is now in the compiler.
Oh, part of the answer is capabilities, but since I can't talk to you about that at the moment, it's hard to answer. Capabilities are an answer.
I've been wondering, why is execute and read the same problem?
Well, execute means to be able to execute the program as computer code.
But it's not
And
just like
reading
reading
is
file.
the ability just to be able to read and look at the file. I haven't hit this point. Stop.